Welcome to String Scale Models. I do models. My name is Jason, and I am going to be talking about some more electronics. This is going to be my book series of me trying to learn embedded system design. This is the Embedded System Design textbook by Brock Lemires. It is based on using the MSP 430 FR2355 Launchpad. In the last video I did an overview and a review of what I learned in Chapter 1, and now I am going over what I learned in Chapter 2 and a brief overview of Chapter 2, because once we get out of that, we are actually moving on to the unit itself, the actual launchpad. So this chapter overview is digital logic basics, and if you've seen any of my logic series, I have a understanding of how digital logic works, and I try to explain it to you, but this mainly is talking about converting binary numbers and hexadecimal numbers and all that good stuff. I'm not going to get into that because in the digital logic series there's going to be a whole chapter on the number system, and I will get into the conversions on things like that. But basically, I just want to do a brief overview of the logic in itself. So I'm going to switch to this here. And I'm going to start with, let's talk about a buffer. B-U-F-F-E-R, a buffer. And it basically has this symbol here. And it has an in and an out. Okay, and it has a truth table of in and out of 0 in, 0 out, 1 in, 1 out. Now, and that is, if you want to write out the function, it would be out equals in. So that would be your buffer. Now, digital logic uses ones and zeros. It's either on or off, high or low, in a system that works that way. And these digital logic gates are semiconductors based logic out of different transistors and transistors and diodes and resistors, all crammed into a IC chip. If you look at some of my digital logic series on individual chips, you have a package of like NAND gates, OrGates, or whatever gate that you want to work with. You have a package and it has X amount in there, and then in each one of those gates there is a set number of transistors. I actually have a few videos in the logic series of how to actually build gates with the transistors, but the transistors that I used was just one or two transistors within an IC package that actually has gates built in it, like in the 74 series. It uses resistors and some Schottky diodes. The LS series uses Schottky diodes and things to lower the voltage drops and the quiescent current over the original 74 series. And then you have like a 74 HC series where it uses the CMOS technology, which is a little bit different than transistors, to where you have a pair of N-channel MOSFETs and a pair of an N-channel MOSFET and a P-channel MOSFET, and depending on the signal that is fed in, one side or the other will turn on. So with transistors, you're either turning on transistors or you're not turning on transistors. There's not a cohesion between the two units. Like with CMOS, CMOS is complementary metal oxide semiconductors, so they work off each other. The N channel and the P channel work off each other. So I'll talk about that later, but let's get back to basic gates. And then you have your inverter. You have your inverter or your NOT gate, which means, and this looks like this with a little inversion bubble on it. And I'll start labeling the input A and the output Y, and your table would be A and your output would be Y, and then you would have 0 and 1, and you would have 1 and 0. So it would be the opposite. So you have on your actual function, you would have you would have Y equals the inverse of A, or Y equals A not with a little apostrophe. So I tend to write the inversion bar on the top. Like, I tend to write it this way if I'm writing it out, but if I am typing it on the computer, I have to do it this way because I can't get the little bar on the top there. So let me clear this. Well, let me just move it out of the way here. Okay. So next we have our AND gate and our NAND gate, and then we have NAND gate. Your AND gate looks like this, and your NAND gate looks like an AND gate with the inversion bubble. So we have an A and a B and a Y output, and our truth table is A, B, Y. And then now we could have different combinations. We could have 2 zeros, or a 0 and a 1 and a 0, or a 1 and a 1. And with an AND gate, both inputs, this input and this input, must match to get that corresponding input on the output. So 2 lows or zeros would be a 0. A 0 and a 1 do not match, so that would be a 0. A 1 and a 0 again do not match, but a 1 and a 1 matches. So you would get that symbol, and your function would be Y equals A, B. Now, that is implied that the AB is using multiplication, because the multiplication symbol is your AND symbol. So it would be A dot B, but writing them next to each other is a way of signifying multiplication. So you have your NAND gate, so you have your A, B, and Y, and as you can guess, with the inversion bubble, it is going to be a different table. And pardon my handwriting, I don't have very good handwriting. 0, 0, 0, 1, 1, 0, 0, 0. This is why the number system, so you can count up in binary and know what they are. So since it is the opposite with the NAND gate, it is the opposite of the inputs, unless this is a 1 and a 1, unless they match. So right now, if you have a 0 and 0, you will get the opposite out, which is a 1. And if you have a 0 and a 1, that is not turned on, so that will be a 1. And a 1 and a 0 will be a 1. And then 2 1s will actually give you the low. So this is Y equals A, B inverse. So not the inverse of A or not the inverse of B. It has to cover the whole unit. You can also write it as Y equals A times B, put it in parentheses, and then not the whole thing. So that is a way of doing it. So if you don't want to put the bar on the top, that is a acceptable way of doing it. But you could not do it as Y equals A not B not, because that would not be a NAND gate. That would be this type of gate here. So that would be a NAND gate, an AND gate, because you with an inversion on the front. So you would have A, B, and then you would flip whatever A and B is first, and then you would run it through the AND gate. So that is different than, this is a different way of writing it, so that is not correct. So let's move on to the OrGates. This may be an extremely boring video, guys, so, you know, I'm sorry about that. Can we go over here? There we go. Let's go over here to this side here. So we have our OR gates, which is the AND gates are a logical product. So and then OR is a sum. So we have our OR, and it looks like this. That is our OR gate, and we have A, B, and Y, and then we have A, B, and Y. 0, 0, 0, 1, 1, 0, 1, 1. Now, this is if either or are a high, you're going to get a high, but 2 zeros is not either or. So it would be like this. And then you would have Y equals A plus B. Now, it's not plus, you're not adding, but it is the plus symbol is the symbol for using an OR gate in combinational logic. And it kind of makes sense if you have 0 plus 0 is a 0, and then 0 plus 1 in binary is a 1, 1 plus 0 in binary is a 1, and 1 plus 1 is turns into 0 or 1 0 in binary, because you can't go higher than 2. 1 0 in binary, and 1 0 in binary still has a 1 in it, so it would be a 1 output. So if you did add up the numbers in an OR gate, it would work out to giving you the correct output. And it kind of works that way with the multiplication, but it has some fails. That's just my personal thing. It doesn't talk about that in the book, but that's how I understand it, and it made it easier for me. So if it works for you, if it confuses you, I'm sorry. You have the NOR gate, same symbol, but as you could probably guess, has the inversion bubble. A, B, Y, and then we have A, B, and Y. Then we have 0, 0, 0, 1, 1, 0, 1, 1. And then now, so if either or would be a 0, we have to invert that, so that is a 1. And then if either or of these is a 1, we're going to get a 0. Any one of these is a 1, we're going to get a 0. Any one of these is a 1, we're going to get a 0. And this would be written as Y equals A plus B with a bar over the whole thing, or Y equals A plus B in parentheses with the not, because if you did it Y equals A naught plus B naught, that would be again putting the bubbles on the front of the NOR gate, and that's not how this is written, and it wouldn't read correctly. So that is the OR section of the logic gates. We just have the last two here. We have the XOR, which means exclusively OR, so we have two little things there, and then we come out and A, B, and Y, and then we have A, B, and Y, and again, and then you can actually count. That's 1, that's 2, that would be 3 in binary, and then we have either or, and that would be a 0, and either of these is a 1, so we're going to get a 1, and either of these is a 1, we're going to get a 1. Now these have to be exclusive, so 1 and a 1 are not exclusive, so it only can have one 1 in there, so that would be x0, and this would be written Y equals A, and your plus symbol would have a circle around it, B, and that would be A exclusively ORed with B equals Y, your output. And then you have the X NOR, which is this here with an inversion bubble. So it's basically a NOR gate that's exclusive. A, B, Y, and then you have 0, 0, 0, 1, 1, 0, 1, 1, and then this will be a 1, this will be a 0, 0, and a 1, because this would normally be a 0 and you flip it with the inversion. So this would be Y equals A exclusive ORed with B with a not symbol, or Y equals A exclusive ORed with B with parentheses and the not symbol. Remember, you can't do the symbol has to go all the way across the top or in parentheses with the not symbol. Now, you can combine these. Let's make some more room here. Okay, let's make some more room. You can combine these, like you can take a AND gate and feed it into a OR gate like this, and then you can have a inverter here, and you can feed that into your OR gate. You can feed a line into your there, and this could be your B, and this could be your A, and then you would have, if you wanted to look at this combinationally, and this is your Y output, you would have, for the first thing you would have is, you would have a B not column, because you have B coming in and it's knotted, so this would be the inverse of B, and then this would be, so this output, we'll say this output is J. So the output of J would be J equals A times B naught. So, ANDed with B naught. So if you were to look at this first section that I drew here as a truth table, you would have A, B, and then you would have Y. And then if you had 0, 0, 0, 1, 1, 0, 1, 1, if you had a truth table, you have to take the inverse of B. So in the first 0, 0, if B was actually a low, it would be a 1. So a 0 and a 1 ANDed together give you a 0. And then if you have if A is 1 and B is a 1, which would be A is a 0 and B is technically a 0 because it's going through the inversion bubble, that would be 2 zeros, which would give you a 0 or a low. And then if you had A is a 1 and B is a 0, which would be inverted through the inversion bubble, that would become a 1, and a 1 and a 1 gives you a 1 output. If you had a 1 and a 1, A would stay a 1 and B would switch to a 0 through the inverter, and 1 and 0 gives you a 0. So the only time that you would have a high output on this here is if A was a 1 and B was a 0. So the actual formula for this AND gate here is J, I already wrote it, my bad, is this formula here. So now if we look at this gate here, we have a J input and then we have a B not input. So if we write down this table here, we have J, B, and then we have our final, this was supposed to be a J, final Y output. And if we go 0, 0, 0, 1, 1, 0, 1, 1, if we do that, so if J is a 0 and B is a 0, B is actually being inverted. So if B is the original B is a 0, it's being inverted, so it's actually a 1. So in an OR gate, we would get a 1 output. Now if J is a 0 and B is a 1, B would be inverted to a 0, so we would have two zeros, so that would be a 0 output. And then J is a 1 and B is a 0, that would be a 1 on J and a 1 on B, which would definitely give us an output. And then a 1 and a 1 would be a 1 on J, and a B would be a 0, so that would be a 1 output also. So this formula would be Y equals J plus B naught. So your whole formula for that would be for that, and then your whole formula would be, if you wrote it out combinational logic, would be Y equals A times B naught plus J plus B naught. So, and then you could use the different properties of algebraic math and jumble this around to bring out the B, and then you could actually come up with a truth table that says when A is a certain input, and then you would get a certain output. I'm not going to get into the algebraic math of this scenario because I struggle. I used to not struggle with math, but I tend to struggle with the math. But I just wanted to give a brief overview of the combinational logic and how you can combine it, and then you can write the formulas out, and then you can write the truth tables out. And then there is actually easier ways to do this. You can look up the math. Brock Lemire's has a YouTube channel, Digital Logic and Programming, and he goes over a whole huge, like 140 something videos on combinational and digital logic, and talking about the different axioms and the Boolean value in the math, and how you can combine and reduce logic gates that it spans over probably 10 or 15 videos. They're 20 minutes long each. I am not going to go into all that. I just wanted to give you a basic overview of logic and how it can be combined combinationally. I mean, there is what is the K maps? I believe it's the Kavanaugh system. Is that right? What is the K maps? Yeah, it just says K map. So the K map, I believe it's Kavanaugh, where you can, shrink down your logic and find the simplest terms, and you have the product of sums and all that stuff. There's a lot of things, and then also with all these logic gates, they can be combined into latches, your SR latch, your T flip-flop, your JK flip-flop, your D flip-flop, your D latch. There's tons of different combinations of these that are then put into what are drawn as function blocks. Let's show you a function block here. This is the next stage of there. So if you have a bunch of AND gates and NAND gates, you would start to see something like this, a function block, and it would have a, for example, this will make this a D flip-flop. So this will be your D input, this will be your CLK input, and we'll put the little thing there so it triggers on a tie pulse. Then you would have something like your Q, and then you would have your Q naught, and then there would be a bunch of logic and SR latch in here, and you would have it simplified, and then you just need to know the properties of a D-latch, and then it can actually get bigger to where you have a set pin, or preset, preset, and then also a reset, and they're active low, so they'll have the bar over it, so when a low signal is applied, they reset. They're normally asynchronous, so they happen whether the clock pulses or not. And this is all part of combinational logic and getting into different things. D flip-flop is used a lot in programming. The FPGA uses tons of D flip-flops, and use it for storage registers and all kinds of stuff. And then we get into, this is a huge chapter, chapter 2 in digital logic basics. It's combinational logic. We get into 4-bit adders, just massive amount of information, and I've gone through it, and I come back and use it as a reference to help me further in the program. Then after you have combinational logic, it goes into sequential logic, which is something I still am grasping on. It's been years since I've had to work with sequential logic with clock pulses and things like that. I am working on it in my digital logic series, and a lot of the stuff that is discussed in this chapter 2 of this embedded systems design book here. Let me go back to this. That is in here. I cover in bits and pieces on my logic series, and like I said before, Brock Lemires does an excellent stuff on his channel. I'll try to link it in the description of this video. I did it in the last one, but chapter 2 is basically combinational logic, sequential logic, the number system. It's a huge chapter in here, but it's getting the background and stuff done you need in order to move forward with the programming of the Launchpad system. So I got through it. It took me a little bit longer to get through it than I wanted to. I just wanted to give a basic overview of the basic logic, and then as I do things later in chapters and do programming and things like that, if stuff comes up like sequential or combinational logic where I have to do math and stuff, I'll go through and show you the different steps. But my digital logic series will be doing a lot of stuff that is covered in chapter 2 when I'm doing each of the chips now, and then I'm going to start doing combining the chips to build different things. Like I'm working on a code cracking game that uses combinational logic and things like that. So that is what's going on. Next is chapter 3, where we learn about the MSP 430 FR 2355 Launchpad. That will be coming up next week. I hope you all enjoyed this video. It was a lot of complication. I hope I explained everything clearly. Let me know in the comments below. If you're not subscribed, subscribe, because I do Switch stuff. I do the traffic light project. I do the code crack project. A lot of different projects going on the channel. A little bit of FPGA programming, but I'm still... I ordered something for it and it hasn't arrived, and then when it did arrive, it was the wrong item. So the FPGA project's on hold, but it will be picked up very soon in the future. Thank you so much, everyone. Here's the links to social media. You can visit my Patreon, where I'll start to be posting stuff on there with my different things. You won't have to join to see it, but it's a website where I can post things until I get my own website up and running. Thank you so much, and have a fantastic day.